Welcome. We're happy to have you join us here at the Z Files, where we drift into the mysteries that fill the night sky and let curiosity guide us gently towards sleep. Now, we turn our gaze outward, far beyond the familiar planets of our solar system, to worlds that orbit distant stars. These are places we cannot visit, not yet, and perhaps not ever. But we can study them. We can wonder about them. And in that wondering, we might find answers to one of humanity's oldest questions. Are we alone? Part 1. The quiet search beyond our world. For centuries, the idea of life on other worlds lived only in stories and speculation. It was the territory of dreamers and writers, a question too vast to answer with the tools we had. But science has a way of turning dreams into data. Today, astronomers peer through telescopes not just to see distant planets, but to read the invisible messages written in their atmospheres. They look for chemical signatures, faint traces of gases that might reveal something extraordinary. They search for biosignatures, the fingerprints of life itself, hidden in the air of worlds we will never touch. Among the thousands of planets discovered beyond our solar system, a particular type has captured the attention of researchers. These are called super-Earths. The name is simple enough. A super-Earth is a planet larger than Earth but smaller than Neptune. Most of them fall somewhere between 1.5 times and about 10 times the mass of our own world. They occupy a middle ground, a category that does not exist in our solar system, yet appears to be common throughout the galaxy. Some orbit close to their stars, baked by intense heat. Others drift farther out, wrapped in cold and shadow. A few, just a few, sit in that delicate zone where temperatures might allow liquid water to exist on their surface. And where there is water, there might be life. But size and location are only part of the story. What truly matters, what determines whether a super-Earth could harbor life, is its atmosphere. An atmosphere is more than just a blanket of air. It is a shield, a regulator, a chemical library. It protects the surface from harmful radiation. It traps heat or lets it escape. It holds the gases that life needs to breathe, to grow, to leave its mark. Without an atmosphere, a planet is just rock and metal, silent and sterile. With one, it becomes a world of possibility. Understanding these atmospheres is no simple task. We cannot travel to these planets. We cannot land probes on their surfaces or scoop samples of their air. Instead, we rely on indirect methods, on light and mathematics, on the subtle ways a planet alters the starlight that passes through or bounces off its atmosphere. Scientists study the spectrum of that light, searching for the telltale signs of specific molecules. Oxygen, methane, water vapor, carbon dioxide. Each gas absorbs light in its own unique way, leaving dark lines or bright peaks in the data. By reading those patterns, researchers can begin to sketch a portrait of a world they will never see up close. The composition of an atmosphere tells us what a planet is made of and what processes might be happening on its surface or in its skies. But composition alone is not enough. Atmospheres are not static. They change. They leak. Over time, gases escape into space, stripped away by stellar winds or blown off by intense radiation. A planet's gravity tries to hold on, but it does not always succeed. The balance between retention and loss shapes everything. A thick atmosphere might create a runaway greenhouse effect, turning a world into a pressure cooker like Venus. A thin one might leave the surface exposed and frozen, like Mars. Somewhere in between lies the narrow band of conditions we call habitable. Super-Earths, with their greater mass and stronger gravity, hold onto their atmospheres more tightly than smaller worlds. This makes them especially interesting. If they formed with the right mix of gases, if they orbit at the right distance from their star, if their magnetic fields are strong enough to deflect the solar wind, then they might maintain stable atmospheres over billions of years. Long enough for life to begin. Long enough for that life to change the air around it, to leave chemical clues that we might one day detect. The search for these clues is not just a matter of looking. It is a matter of listening, of patience, of waiting for the right moment when a planet passes in front of its star and we can catch a glimpse of the light filtering through its atmosphere. It is detective work on a cosmic scale, piecing together evidence from photons that have traveled for years or centuries to reach our telescopes. And in that evidence, scientists hope to find something unmistakable. A gas that should not be there unless something living is producing it. A signature that whispers across the void. You are not alone. As we drift deeper into this topic, we will explore the delicate physics that governs these distant skies, the methods that allow us to read them, and the tantalizing possibility that one day, in the data streaming back from a telescope, we might find proof of life beyond Earth. But we will also consider a quieter, more uncertain question. If we do find that proof, if we do confirm that life exists on a super-Earth or any other world, what then? The late physicist Stephen Hawking once warned that we should be cautious in our search, that contact with advanced extraterrestrial life might not go as we hope. As we peer into these atmospheres, deciphering whispers of alien life, we cannot know if we are looking for potential friends or something else entirely. For now, let us settle into the science, into the slow unfolding of discovery, and see where the evidence leads. Part 2. How atmospheres fade and what holds them close. An atmosphere is a fragile thing. It might seem permanent, a constant presence wrapping a planet like a second skin, but it is always in motion, always changing. Gases drift upward from the surface, heated by the sun, jostled by radiation, pulled by gravity, pushed by the solar wind. Some of those gases escape. They slip away into space, molecule by molecule, never to return. Over millions or billions of years, this slow leak can reshape a world. A thick atmosphere can become thin. A wet planet can become dry. The difference between a living world and a dead one can come down to how well a planet holds onto its air. There are several ways an atmosphere can lose its grip. The most straightforward is thermal escape. This happens when gas molecules in the upper atmosphere move fast enough to break free from the planet's gravity. Temperature drives this process. The hotter the gas, the faster the molecules move. If they reach a speed called escape velocity, they simply drift away. Light gases like hydrogen and helium are especially vulnerable because their molecules are small and quick. Heavier gases like nitrogen and oxygen are slower and less likely to escape on their own, but even they can be lost under the right conditions. Another force at work is stellar wind stripping. Stars do not shine in silence. They pour out streams of charged particles, protons and electrons, that race through space at hundreds of kilometers per second. When this solar wind collides with a planet, it can peel away the outer layers of the atmosphere, especially if the planet lacks a strong magnetic field to deflect the particles. Earth has such a field, generated by the churning of molten iron in its core. This invisible shield pushes the solar wind aside, protecting our atmosphere. Mars once had a magnetic field too, but it faded billions of years ago. Without that protection, the solar wind slowly eroded the Martian atmosphere, leaving behind the thin, cold veil we see today. Photochemistry also plays a role. This is the process by which high-energy light, especially ultraviolet radiation from a star, breaks apart molecules in the atmosphere. When UV light hits a water molecule, for example, it can split it into hydrogen and oxygen. The hydrogen, being light, escapes. The oxygen might react with rocks on the surface or combine with other gases. But over time, this process can drain away water vapor and alter the chemical balance of the air. Photochemistry is not just destructive. It also creates new molecules, some of which might be signs of life. But the balance matters. Too much radiation, too much splitting and stripping, and a planet loses the very gases that could support biology. The rate at which a planet loses its atmosphere depends on several factors. Mass is crucial. A more massive planet has stronger gravity, which makes it harder for gases to escape. This is one reason super-Earths are so intriguing. Their extra mass gives them a better chance of holding onto thick atmospheres over the long haul. But mass is not everything. The type of star a planet orbits matters too. A large, hot star pumps out more radiation and a stronger stellar wind, putting more pressure on the atmosphere. A small, cool star like a red dwarf is gentler in some ways, but it can also flare unpredictably, sending bursts of energy that strip away gases in sudden pulses. Distance from the star is another key variable. A planet that orbits too close is bathed in intense heat and radiation. Its atmosphere heats up, the gas molecules speed up, and thermal escape accelerates. A planet too far out might avoid this fate, but it risks freezing, with gases condensing into frost on the surface rather than floating free. The habitable zone, that narrow orbital range where liquid water can exist, is not just about temperature. It is also about finding the sweet spot where atmospheric loss is slow enough for a stable environment to persist. Magnetic fields add another layer of protection. A planet with a strong magnetic field can deflect much of the stellar wind, reducing the rate of atmospheric stripping. The strength of that field depends on what is happening deep inside the planet. A molten metallic core, spinning and convecting, generates the field through a process called a dynamo. If the core cools and solidifies, the dynamo shuts down, and the magnetic shield weakens. Scientists are still working to understand which super-Earths might have active dynamos and which might be vulnerable. It is one more piece of the puzzle, one more variable in the equation of habitability. So how do we study these distant atmospheres when we cannot visit them or sample them directly? We rely on light. When a super-Earth passes in front of its star, a tiny fraction of the starlight filters through the planet's atmosphere before reaching us. Different gases absorb different wavelengths, leaving dark lines in the spectrum. By comparing the spectrum during the transit to the spectrum when the planet is out of the way, astronomers can identify which gases are present. This technique is called transit spectroscopy. It is painstaking work. The signals are faint, often buried in noise, but with careful observation and powerful telescopes, the data begins to reveal itself. Direct imaging is another method, though it is even more challenging. This involves blocking out the light from the star and capturing the faint glow of the planet itself. The atmosphere reflects and emits light, and by analyzing that light, scientists can learn about its composition and temperature. Only the brightest, largest planets orbiting far from their stars can be imaged this way, but the technique is improving. Future telescopes, equipped with advanced instruments and larger mirrors, will be able to see smaller, more Earth-like worlds. Phase curves offer a third approach. As a planet orbits its star, The amount of light we see from it changes depending on its position. By measuring these subtle variations over time, researchers can map the distribution of heat and gases across the planet's surface and atmosphere. A planet with a thick atmosphere will redistribute heat more evenly than one with a thin atmosphere or no atmosphere at all. These patterns tell a story about wind, clouds, and the movement of air from day side to night side. Each of these methods has its limitations. Each requires patience, precision, and a bit of luck. But together, they are giving us our first real glimpses of alien skies. We are learning which gases are common, which are rare, and which might be signatures of life. We are beginning to see how atmospheres behave, how they respond to their stars, and how they change over time. And with each new observation, the picture becomes a little clearer. Imagine standing on the surface of a super-Earth, if you could. Above you, the sky might glow in colors we have no names for, tinted by gases we have never breathed. The air might press down heavier than anything you have felt on Earth, or it might be so thin that sound barely carries. The sun, if you could call it that, might be a fierce white point or a dull red ember, depending on the star you orbit. And in that sky, unseen, molecules drift and collide, split and recombine, leaving traces that someday, someone light years away might detect and wonder about. That is the strange intimacy of this science. We touch these worlds only with light, only with data, but the connection is real. As we move forward, we will turn our attention to the specific gases that might signal life, the biosignatures that researchers hope to find, and the tantalizing question of habitability. But we will also keep in mind the possibility that what we discover might not be simple. Life, if it exists out there, might be stranger than we expect. And the act of looking, of announcing our presence through our observations and our signals, carries its own uncertainties. Stephen Hawking believed that advanced civilizations might not be kind. As we search for life, we must also ask ourselves what we are inviting, what we are risking, and whether the truth we seek is one we are prepared to face. For now, let us rest in the knowledge that the search continues, patient and steady, one spectrum at a time. Part 3. The gases that whisper life. If we are to find life on a distant world, we will not see it directly. We will not watch microbes swimming in alien oceans or forests swaying under unfamiliar suns. What we will see, if we are lucky and patient, are the chemical consequences of that life. The traces it leaves in the air. The gases it produces or consumes in ways that cannot be explained by geology or photochemistry alone. These are biosignatures, and they are the holy grail of exoplanet research. On Earth, life has transformed the atmosphere over billions of years. Our air is about 21% oxygen, a concentration that would not exist without photosynthesis. Plants, algae, and certain bacteria absorb carbon dioxide and water, harvest energy from sunlight, and release oxygen as a byproduct. This process has been running for so long that oxygen has saturated the oceans, the soil, and the sky. It reacts with rocks, rusts iron, fuels fires, and keeps animals like us alive. Without life constantly replenishing it, atmospheric oxygen would disappear in a geological blink, consumed by chemical reactions with the surface. So when astronomers think about biosignatures, oxygen is often the first gas that comes to mind. But oxygen alone is not enough. It can be produced by non-biological processes too. Ultraviolet light can split water molecules, freeing oxygen and allowing hydrogen to escape. On a planet with no life, this could create a false positive, a misleading hint of biology where none exists. To be confident, scientists need to detect oxygen alongside other gases, a combination that together tells a more convincing story. Methane is one such gas. On Earth, methane is produced by microbes in swamps, in the guts of animals, in decomposing organic matter. It also seeps from geological sources like volcanoes and deep-sea vents. By itself, methane does not prove life. But methane and oxygen together create a puzzle. These two gases react with each other readily. In an atmosphere, they should destroy each other over time unless something is constantly replenishing them. On Earth, that something is life. Microbes produce methane. Plants produce oxygen. The two gases coexist in a delicate, dynamic balance. Finding that same balance on a super-Earth would be a strong clue. Water vapor is another piece of the puzzle. Life as we know it requires liquid water. Detecting water vapor in an atmosphere does not mean life is present, but it does mean water is cycling through the environment, evaporating from oceans or lakes, condensing into clouds, falling as rain. It suggests a climate where water can remain liquid at the surface, at least some of the time. Water vapor, oxygen, and methane together would form a compelling trio, a chemical signature that would be hard to explain without invoking biology. Other gases might serve as biosignatures too. Phosphine, a molecule made of phosphorus and hydrogen, is produced by anaerobic bacteria on Earth. It was recently detected in the atmosphere of Venus, sparking excitement and debate. If confirmed, and if non-biological sources can be ruled out, phosphine could be a marker of microbial life even in extreme environments. Dimethyl sulfide is another candidate. It is produced by marine phytoplankton and has been proposed as a detectable biosignature on ocean-covered worlds. Nitrous oxide, produced by soil bacteria, might also be detectable with the right instruments. The challenge is that none of these gases are foolproof. Nature is inventive. Geological processes, atmospheric chemistry, and stellar radiation can mimic the signs of life. A planet with active volcanoes might release methane. A planet with a hydrogen-rich atmosphere might produce phosphine through high-temperature reactions. Oxygen might build up slowly from water photolysis even without plants. To avoid false positives, scientists must study the full context. They must model the planet's geology, its climate, its history. They must consider whether the concentrations of gases make sense, whether they are stable or fluctuating, whether they fit the profile of a living world or merely an unusual one. This is where the concept of disequilibrium comes in. A disequilibrium signature is a chemical imbalance that should not persist unless something is actively maintaining it. Life is a master of disequilibrium. It takes in simple molecules and energy, rearranges them, and spits out waste products that would not exist in a sterile, equilibrium-driven system. The presence of gases that should react away but do not, that coexist in ratios that make no sense from a purely chemical standpoint, that is the kind of signature that makes scientists sit up and take notice. It is the difference between a planet that follows the rules and one that is breaking them, quietly and persistently, in the way that only life can. Super-Earths offer unique opportunities for detecting biosignatures. Their larger size means more atmosphere to study, more signal to capture during a transit. Their stronger gravity can hold onto lighter gases like hydrogen, which might amplify spectroscopic features and make detection easier. Some super-Earths orbit small red dwarf stars, which are dimmer and cooler than our Sun. This makes the planet-to-star contrast higher, which can improve the chances of detecting faint atmospheric signals. Red dwarfs are also incredibly common, making up about 70% of the stars in our galaxy. If even a fraction of their super-Earths are habitable, the number of potential targets is staggering. But red dwarfs come with their own complications. They tend to be active, prone to flares that blast their planets with radiation. A super-Earth in the habitable zone of a red dwarf orbits very close to its star, often closer than Mercury orbits our Sun. This proximity means the planet is likely tidally locked, with one side always facing the star and the other in perpetual darkness. The day side might be scorching, the night side frozen. If an atmosphere is thick enough, it might redistribute heat through powerful winds, creating a twilight zone between the extremes where conditions could be more moderate. But if the atmosphere is thin or has been stripped away by stellar flares, the planet might be uninhabitable despite being in the so-called habitable zone. These are the subtleties that make each discovery a puzzle, each observation a step toward understanding. There is also the question of how life might differ from what we know. Earth's biosignatures are based on Earth's biology, which is the only example we have. But life elsewhere might use different chemistry, different metabolic pathways, different waste products. A super-Earth with ammonia oceans instead of water might host organisms that produce entirely different gases. A world with a thick hydrogen atmosphere might harbor life that metabolizes in ways we have not imagined. The challenge is to remain open to surprises while not abandoning rigor. Scientists must search for the biosignatures they can predict while staying alert for anomalies that might hint at the truly alien. As we sift through the data, as we catalog the gases in these distant skies, we are essentially learning a new language. Each spectrum is a sentence, each absorption line a word. Some words we recognize, others are mysteries. And somewhere in that vocabulary, if we are patient and clever, we might find the phrase that changes everything. The confirmation that life exists beyond Earth. That we are not the only experiment the universe has conducted. That biology is not a fluke but a feature, woven into the fabric of the cosmos wherever conditions allow. But even as we search with hope, we must remember the caution that Stephen Hawking voiced. If we find life, and if that life is complex enough, intelligent enough, to have its own civilizations, its own technologies, we cannot assume it will be friendly. History on Earth shows that when two civilizations with vastly different levels of technology meet, the results are often devastating for the less advanced. Hawking worried that announcing our presence, seeking contact, might be a mistake. That we might be children shouting into a dark forest, unaware of what might hear us. This is not a reason to stop searching, but it is a reason to proceed thoughtfully, to ask not just can we find life, but should we, and what comes next if we do. For now, we are still in the listening phase, still learning to read the messages written in starlight. And that, perhaps, is where we should be. Patient, curious, careful. Part 4. The habitability equation and the zones between. Finding biosignatures is only part of the story. Before life can leave its mark on an atmosphere, conditions must be right for life to exist in the first place. This brings us to the concept of habitability, a term that sounds simple but hides layers of complexity. Habitability is not a yes or no proposition. It is a spectrum, a probability, a set of overlapping conditions that together determine whether a planet can support life as we understand it. The most familiar concept in habitability is the habitable zone, sometimes called the Goldilocks zone. This is the orbital distance from a star where temperatures are neither too hot nor too cold, where liquid water can exist on a planet's surface. Too close to the star, and water boils away. Too far, and it freezes into ice. The width and location of the habitable zone depend on the star's brightness and temperature. A hot, luminous star pushes the habitable zone farther out. A cool, dim star brings it closer in. For a star like our Sun, the habitable zone stretches roughly from the orbit of Venus to the orbit of Mars. Earth sits comfortably in the middle, which is why we have oceans and rain and life. But the habitable zone is only a starting point. It assumes a planet has the right kind of atmosphere to begin with, one that can trap heat through the greenhouse effect but not so much that it creates a runaway scenario. It assumes the planet has water to begin with, delivered by comets or asteroids or trapped in minerals during formation. It assumes the planet's orbit is stable, not wildly elliptical, so that temperatures do not swing to extremes over the course of a year. And it assumes the star itself is stable, not so prone to flares and radiation bursts that it strips away the atmosphere or sterilizes the surface. Super-Earths complicate this picture in interesting ways. Their larger mass means more internal heat, more volcanic activity, more outgassing of chemicals from the interior. This can replenish an atmosphere over time, counteracting some of the losses to space. But it can also lead to a thicker, denser atmosphere that traps too much heat, creating a Venus-like greenhouse even at distances where Earth-like conditions should prevail. The balance between atmosphere thickness and surface temperature is delicate. A planet with twice Earth's mass might have an atmosphere twice as thick, or 10 times as thick, depending on how it formed and how much gas it captured during its early years. This makes predictions difficult. Two super-Earths at the same distance from similar stars might have radically different climates. Water is another variable that shifts the habitability equation. A planet can have too much water just as easily as too little. A world entirely covered in deep oceans might lack the rock-water interface where many key chemical reactions occur. On Earth, the interaction between water, rock, and atmosphere drives the carbonate silicate cycle, a feedback loop that regulates carbon dioxide levels and stabilizes the climate over millions of years. Rain erodes rocks, washing minerals into the sea. Marine organisms use those minerals to build shells. When they die, their shells sink and eventually get subducted into the mantle, where they melt and release carbon dioxide back into the atmosphere through volcanoes. This cycle acts as a thermostat, keeping Earth's temperature within a range that allows life to persist. A super-Earth without exposed continents might lack this cycle, leading to runaway greenhouse effects or ice ages with no natural correction. The composition of the planet itself matters too. A super-Earth made mostly of rock and iron, like Earth but larger, is different from one made of rock and ice, or rock and water, or even stranger combinations. Some super-Earths might be ocean worlds with hundreds of kilometers of liquid water above a high-pressure ice layer, with no solid surface to speak of. Others might be more like scaled-up versions of Earth, with continents and shallow seas. Still others might be dry, desert worlds with only traces of water locked in polar ice or underground aquifers. Each type presents different possibilities for habitability and different challenges for detecting life. Magnetic fields enter the equation again here. A strong magnetic field does more than protect the atmosphere from stellar wind. It also shields the surface from harmful cosmic rays, high-energy particles that can damage biological molecules and make life difficult or impossible. Earth's magnetic field deflects most of these particles, creating a radiation environment where life can thrive. A super-Earth without a magnetic field might still be habitable if its atmosphere is thick enough to absorb the radiation, but the surface conditions would be harsher. Life might be restricted to underground environments or deep oceans, places where the radiation cannot reach. This would make biosignatures harder to detect, since most of our methods probe the atmosphere rather than the subsurface. Stellar activity is one of the biggest uncertainties. Red dwarf stars, the most common targets for super-Earth habitability studies, are known for their flares. These are sudden, intense bursts of radiation and charged particles that can be thousands of times more powerful than anything our Sun produces. A flare can temporarily strip away part of a planet's atmosphere, bombard the surface with ultraviolet and X-ray radiation, and disrupt any chemistry happening in the air. If flares are frequent enough, they might prevent life from ever gaining a foothold. But recent research suggests that some planets might be resilient. A thick atmosphere, a strong magnetic field, and rapid atmospheric replenishment from volcanic outgassing could allow a planet to weather the flares and remain habitable. The question is whether this resilience is common or rare. Tidal locking adds another layer of complexity. A super-Earth orbiting close to a red dwarf is likely to be tidally locked, meaning one side always faces the star and the other is always dark. This creates extreme temperature gradients. The day side might be hot enough to boil water. The night side might be cold enough to freeze carbon dioxide. In between, at the terminator line where day meets night, conditions might be more temperate. If the atmosphere is thick and dynamic, it could transport heat from the day side to the night side through powerful winds, creating a more uniform climate. Some models suggest that such a planet might have a permanent storm on the day side, where hot air rises, and a perpetual high-pressure zone on the night side, where cold air sinks. Life might exist in the twilight regions, or it might adapt to the extremes in ways we have not considered. There is also the matter of time. Habitability is not static. A planet that is habitable today might not have been habitable a billion years ago, or might not be habitable a billion years from now. Stars evolve. They brighten as they age. The habitable zone shifts outward over time. A planet that starts out on the inner edge of the habitable zone might eventually become too hot as its star brightens. Conversely, a planet on the outer edge might thaw and become habitable later in its star's life. Tectonic activity slows as a planet's interior cools. Volcanic outgassing decreases. Magnetic fields weaken or vanish. Atmospheres thin. The window of time during which a planet is habitable might be narrow, measured in hundreds of millions or billions of years, but not indefinite. This is where the search for biosignatures intersects with the question of intelligence. If life arises on a super-Earth, how long does it take to evolve? On Earth, single-celled organisms appeared relatively quickly, within the first billion years of the planet's history. But complex, multicellular life took much longer. Intelligent life, capable of technology and communication, arose only in the last few million years. If the same timelines hold elsewhere, then most habitable planets might host only simple life, microbes that produce biosignatures but nothing more. Advanced civilizations might be vanishingly rare, separated by vast distances and vast stretches of time. The universe might be full of life but empty of voices. Or it might not. Perhaps intelligence evolves more quickly under different conditions. Perhaps the circumstances that make a super-Earth habitable also favor complexity. Or perhaps, as Stephen Hawking suggested, intelligence has already arisen many times, and some civilizations have endured for millions or billions of years, growing in power and reach, becoming something we cannot yet imagine. If such beings exist, they might have their own reasons for remaining silent, for watching without revealing themselves. And we, peering into the atmospheres of distant worlds, might be the ones being watched. The habitability equation is vast and uncertain, but it is also the framework that guides our search. It tells us where to look, which planets to prioritize, which spectra to study most carefully. And as our instruments improve, as our telescopes grow larger and our models more sophisticated, the equation becomes a little less uncertain. We are learning what makes a world habitable. And in learning that, we are also learning what it means to be alive in this universe, one small part of a much larger, much stranger whole. Let us carry these questions forward, gently, as we consider the tools and missions that are bringing these distant worlds into focus. Part 5. The instruments that read distant skies. To search for life on worlds we cannot visit, we need telescopes unlike any that came before. Not just larger mirrors or sharper lenses, but instruments designed specifically to tease out the faint chemical signatures hidden in starlight. Over the past few decades, astronomers have built a suite of tools that are transforming exoplanet science from speculation into observation. Each new telescope, each new spectrograph, brings us closer to answering the question of whether we are alone. The story begins with the Hubble Space Telescope, launched in 1990 and still operating today. Hubble was not designed to study exoplanets. When it launched, we had not yet discovered a single planet orbiting another sun-like star. But as the field exploded in the 1990s and 2000s, astronomers realized that Hubble could do something remarkable. It could capture the spectrum of an exoplanet's atmosphere during a transit. The first successful atmospheric detection came in 2001, when Hubble observed sodium in the atmosphere of a hot Jupiter, a giant planet orbiting close to its star. The signal was faint, the analysis painstaking, but it proved the concept. We could read the air of another world from across light years. Since then, Hubble has studied dozens of exoplanet atmospheres. It has found water vapor, methane, carbon dioxide, and other gases. It has shown us worlds wrapped in high-altitude hazes, planets with clouds made of silicate minerals, atmospheres that are clear or opaque depending on their chemistry. Hubble's observations have been foundational, but the telescope has limits. Its mirror is only 2.4 meters across. Its instruments, though upgraded over the years, were not optimized for exoplanet work. To go deeper, to study smaller planets, to search for biosignatures, we needed something better. That something arrived in 2021. The James Webb Space Telescope, often called JWST or simply Webb, is the most powerful observatory ever launched. Its primary mirror is 6.5 meters across, nearly 3 times the diameter of Hubble's, giving it far more light-gathering power. It observes in infrared wavelengths, which are ideal for studying exoplanet atmospheres. Infrared light can penetrate dust, reveal heat signatures, and detect molecules that are hard to see in visible light. Webb is stationed at a point in space called L2, about 1.5 million kilometers from Earth, where it can observe continuously without interference from our planet's heat or light. Webb's first exoplanet observations have already delivered surprises. It has detected carbon dioxide in the atmosphere of a hot gas giant, a clear, unambiguous signal that would have taken dozens of Hubble observations to achieve. It has studied rocky planets around a nearby red dwarf, finding that some have atmospheres while others have been stripped bare by stellar radiation. It has begun surveying super-Earths, measuring their atmospheric compositions, searching for water vapor, methane, and other key gases. Each observation adds data to the growing catalogue of alien worlds, and each dataset is scrutinized by researchers around the globe, looking for patterns, anomalies, signs of life. But Webb, as powerful as it is, cannot do everything. It is one telescope, and there are thousands of exoplanets to study. It is optimized for infrared observations, which means it cannot see certain spectral features that are visible in ultraviolet or optical light. And it is expensive, with observing time allocated in tiny increments to teams who have competed fiercely for the opportunity. To fully characterize exoplanet atmospheres, to search systematically for biosignatures, we need a fleet of telescopes, each designed for a specific task. On the ground, enormous observatories are being built to join the search. The Extremely Large Telescope, or ELT, is under construction in Chile. When complete, it will have a mirror 39 meters across, composed of 798 individual segments working together. It will be able to directly image exoplanets, capturing their light separately from the glare of their stars. It will measure atmospheric compositions with unprecedented precision. The giant Magellan telescope, also in Chile, will have a mirror 25 meters across. The 30-meter telescope, planned for Hawaii, will add another powerful eye to the sky. These giants will work in tandem with space telescopes, covering different wavelengths, cross-checking results, building a comprehensive picture of each target planet. Spectrographs are the heart of this effort. A spectrograph is an instrument that splits light into its component wavelengths, creating a spectrum that can be analyzed for the fingerprints of atoms and molecules. Different designs are optimized for different tasks. High-resolution spectrographs can detect tiny shifts in spectral lines caused by a planet's motion or rotation. Low-resolution spectrographs gather more light, making them better for faint targets. Some spectrographs operate in visible light, others in infrared or ultraviolet. The best observations combine data from multiple spectrographs, piecing together a complete picture from fragments of information. Transit spectroscopy remains the workhorse technique. When a planet crosses in front of its star, a small fraction of the star's light passes through the planet's atmosphere. Gases in that atmosphere absorb specific wavelengths, leaving dark lines in the spectrum. By comparing the in-transit spectrum to the out-of-transit spectrum, astronomers can isolate the atmospheric signal. The challenge is that the signal is tiny, often just a few parts per million of the total starlight. Noise from the telescope, from the Earth's atmosphere, from the star itself, can easily drown it out. Success requires careful calibration, repeated observations, and sophisticated data analysis. Direct imaging is harder but more rewarding. By blocking out the star's light with a device called a coronagraph, astronomers can capture the faint glow of the planet itself. The planet reflects some of the star's light and emits its own thermal radiation, creating a spectrum that reveals atmospheric composition, temperature, and even surface features if the planet is close enough and the observations sharp enough. Direct imaging works best for large planets orbiting far from their stars, where the contrast between planet and star is highest. But as coronagraph technology improves, smaller and closer planets are coming into view. Future missions may be able to directly image super-Earths in the habitable zone, capturing their light and reading their atmospheres in a single observation. Phase curve analysis adds another dimension. As a planet orbits its star, the amount of light we see from it changes. When the planet is behind the star, we see nothing. When it is in front, we see the transit. When it is to the side, we see the day side reflecting starlight. By measuring these variations over a complete orbit, astronomers can map the distribution of heat and light across the planet's surface. A planet with a thick atmosphere will have a smooth phase curve, with heat redistributed evenly. A planet with no atmosphere, or a thin one, will have sharp contrasts, with the day side bright and the night side dark. This technique has been used to study hot Jupiters and is now being applied to smaller, cooler planets. Each method has its strengths and weaknesses. Each requires different instruments, different observing strategies, different amounts of time. The art of exoplanet science is knowing which method to use for which planet, how to combine data from multiple observations, and how to extract the maximum amount of information from every photon that reaches our detectors. It is slow work, meticulous work, but it is yielding results. We are building a library of exoplanet atmospheres, cataloging their compositions, their temperatures, their structures. And somewhere in that library, perhaps soon, we will find the entry that changes everything. There are also missions on the horizon designed specifically to search for biosignatures. The Habitable Worlds Observatory, still in the early planning stages, aims to directly image dozens of Earth-like planets and super-Earths, studying their atmospheres for signs of oxygen, methane, water vapor, and other key gases. The LIFE mission, proposed by European scientists, would use a fleet of infrared telescopes flying in formation to achieve the sensitivity needed to detect biosignatures on rocky planets around nearby stars. These missions are years, perhaps decades, away from launch, but the technology is being developed now, tested on existing telescopes, refined with each new observation. The search for life is no longer abstract. It is engineering. It is optics and electronics and data processing. It is choosing which stars to observe, which planets to prioritize, which wavelengths to measure. It is analyzing terabytes of data, searching for signals buried in noise, checking and rechecking results to rule out errors. It is collaboration between hundreds of scientists, each contributing a piece of the puzzle. And it is happening now, night after night, as telescopes across the world and in space turn toward distant stars and collect the light that has traveled for years to reach us. As we continue, we will consider the specific targets, the super-Earths that have captured our attention, and what we have learned about them so far. But we will also hold in our minds the question that lingers beneath every observation. If we find what we are looking for, if we detect unmistakable signs of life, what then? The search is thrilling, but the answer, when it comes, may be more complex than we hope. Part 6. The candidates we are watching. Not all super-Earths are created equal. Some are too hot, their atmospheres boiled away or thick with caustic clouds. Some are too cold, frozen and silent. Some orbit stars too violent or too dim. But a few, a precious few, sit in that narrow band of conditions where life seems possible. These are the world's astronomers return to again and again, refining their measurements, adding new data, building a portrait one observation at a time. They are not yet proven to be habitable, let alone inhabited, but they are the best candidates we have. And so we watch them. One of the most famous is Proxima Centauri b. It orbits Proxima Centauri, a red dwarf star just over 4 light-years away, the closest star to our Sun. Proxima b is a super-Earth, slightly more massive than our own planet, and it orbits within the habitable zone of its star. At first, this sounded like the Holy Grail, a potentially habitable world practically in our backyard. But the details complicate the picture. Proxima Centauri is an active star, prone to frequent and powerful flares. These flares bombard the planet with radiation, likely stripping away any atmosphere it might once have had. Early observations suggested the planet might be airless, a rocky husk baked by stellar wind. But more recent studies hint that it might have a thin atmosphere after all, perhaps replenished by volcanic outgassing. The jury is still out. Proxima b remains a target of intense interest, but it may not be the paradise we initially hoped for. Then there is the TRAPPIST-1 system, a red dwarf about 40 light-years away with 7 Earth-sized planets, at least 3 of which orbit in the habitable zone. These are not quite super-Earths by the strictest definition, as they are close to Earth's size rather than significantly larger, but they occupy the same conceptual space. TRAPPIST-1e, in particular, has drawn attention. It sits squarely in the middle of the habitable zone, receives about the same amount of light from its star as Earth does from the Sun, and may have a rocky surface with liquid water. Early observations with Webb have revealed that some of the TRAPPIST-1 planets lack thick hydrogen atmospheres, which is good news, as thick hydrogen would make them more like mini-Neptunes than rocky worlds. But detecting thinner, more Earth-like atmospheres is harder and requires more observing time. The system is a priority target for multiple telescopes, and over the next few years, we will learn much more about whether any of these worlds have the air and water needed for life. K2-18b is another intriguing case. This super-Earth orbits a red dwarf about 120 light-years away and lies within the habitable zone. It is larger than Earth, with a mass about 9 times greater, and recent observations have detected water vapor in its atmosphere. This was a significant finding, the first detection of water on a planet in the habitable zone of a star other than our Sun. But K2-18b is likely not a rocky world like Earth. Its density suggests it may be a water world, with a deep ocean covering a high-pressure ice layer, and possibly a thick hydrogen-rich atmosphere above that. Such a planet might not have the rock-water interactions that stabilize Earth's climate, and the high pressure at depth might prevent life as we know it. Still, the presence of water vapor is encouraging, and scientists are working to determine whether the planet also has methane, carbon dioxide, or other gases that could shed light on its habitability. LHS 1140b is yet another candidate, a super-Earth orbiting a red dwarf about 40 light-years away. It is denser than K2-18b, suggesting a rocky composition, and it orbits well within the habitable zone. Early models suggested it might be a water world, but more recent observations hint at a thinner atmosphere and possibly exposed rock. The planet is a prime target for Webb, and astronomers hope to detect water vapor, carbon dioxide, or even biosignatures in its atmosphere. Its star is quieter than Proxima Centauri, with fewer flares, which increases the chances that the planet has retained a stable atmosphere over billions of years. There are others, too. TOI 700d, a planet slightly larger than Earth orbiting a red dwarf 100 light-years away, sits in the habitable zone and may have an atmosphere conducive to liquid water. Kepler 452b, a super-Earth orbiting a Sun-like star 1,400 light-years away, is sometimes called Earth's cousin because it receives a similar amount of light and has a similar orbital period. It is too far away for detailed atmospheric studies with current technology, but it remains a tantalizing target for future missions. Each of these worlds is a unique experiment, a different set of conditions, a different roll of the dice in the cosmic lottery of habitability. What makes these planets so compelling is not just their location in the habitable zone, but the possibility that we might actually be able to study them in detail. Distance matters. A planet 40 light-years away is 100 times closer than one 4,000 light-years away, and that makes an enormous difference in the strength of the signals we can detect. Brightness matters too. A planet orbiting a dim star is easier to study than one orbiting a bright star, because the contrast between planet and star is greater. Size matters. A larger planet has a thicker atmosphere, more gas to absorb starlight, a stronger signal in the spectrum. The ideal target is a large, nearby super-Earth orbiting a small, quiet star in the habitable zone. Such planets are rare, but not impossibly so. We have found a handful already, and more are being discovered each year. The process of studying these planets is iterative. First, a planet is detected, usually by the transit method, where repeated dips in a star's brightness reveal the presence of an orbiting body. Then its size and mass are measured, allowing scientists to calculate its density and infer its composition. Then comes the atmospheric reconnaissance, the first rough spectra that tell us whether the planet has an atmosphere at all and what its major constituents might be. Then come deeper observations, looking for rarer gases, for signs of clouds or hazes, for temperature variations across the surface. Finally, if the planet seems promising, it becomes a priority target for the most powerful telescopes, the ones that can search for biosignatures. This can take years or decades. Each step requires new observations, new proposals, new allocations of precious telescope time. Not every candidate will pan out. Some will turn out to have thick, hydrogen-rich atmospheres that make them inhospitable. Some will be airless, their surfaces blasted by radiation. Some will have atmospheres rich in carbon dioxide or sulfur compounds, too toxic for life as we know it. But even the disappointments teach us something. They tell us what does not work, what conditions are hostile, what factors rule out habitability. They narrow the search, refining our understanding of what makes a planet truly Earth-like. And then there is the question of what we do if we find something. If one of these super-Earths shows clear signs of oxygen and methane in disequilibrium, if the spectral lines match the profile of a living world, if the data survives scrutiny and independent verification, then we will have discovered life beyond Earth. It will not be a close encounter. We will not meet these beings, will not exchange messages or ideas. They may be microbes, nothing more, floating in alien seas or clinging to rocks beneath a foreign sky. But it will still be life. It will still mean we are not alone. Stephen Hawking worried about this moment. He believed that the discovery of life elsewhere, particularly intelligent life, might pose a danger to humanity. In his view, an advanced civilization capable of traveling between stars would have technology far beyond ours. And history suggests that when two civilizations meet with vastly different levels of power, the weaker one suffers. He pointed to the colonization of the Americas, the subjugation of indigenous peoples, the spread of disease and exploitation. He wondered if the same might happen on a cosmic scale, if we might attract the attention of something we cannot defend against. Not all scientists share this concern. Many believe that any civilization advanced enough to travel interstellar distances would have moved beyond violence and conquest, that intelligence and empathy go hand in hand. But Hawking's warning remains, a cautionary note in the symphony of discovery. For now, we are only looking. We are not broadcasting powerful signals or sending probes to distant stars. We are listening, observing, measuring. The light we collect from these super-Earths left their atmospheres years or decades or centuries ago, depending on distance. If there is life there, it does not know we are watching. If there are beings there, intelligent or otherwise, They have not reached out to us. We are, for the moment, safe in our ignorance, safe in our distance, learning what we can before we must decide what comes next. The candidates we are watching are more than data points. They are worlds, each with its own story, its own history, its own potential. And as we study them, we are also studying ourselves, asking what it means to be alive, what it means to search for others, and what we hope to find when the search is over. Part 7. The chemistry of hope and uncertainty. When we look at the atmosphere of a super-Earth, we are not just measuring gases. We are reading a story written in molecules, a narrative of how that world came to be and what forces have shaped it over billions of years. Each gas tells part of the tale. Oxygen speaks of photosynthesis or photolysis. Methane whispers of biology or geology. Water vapor traces the journey of hydrogen and oxygen from cosmic clouds to planetary surfaces. Carbon dioxide hints at volcanic activity or the slow weathering of rock. Together, these gases form a chemical signature, a fingerprint that is unique to each world. And in that fingerprint, if we know how to read it, we might find the answer to our deepest question. But chemistry is complicated. Atmospheres are not static mixtures. They are dynamic systems, constantly churning, reacting, evolving. Sunlight drives photochemical reactions that create new molecules and destroy old ones. Lightning splits nitrogen and oxygen, forming nitrogen oxides that dissolve in rain and fertilize soil. Volcanoes inject sulfur and carbon into the air, altering the balance of gases. Ocean spray carries salt and organic molecules into the atmosphere, where they seed clouds and scatter light. Even the surface plays a role, absorbing and releasing gases in cycles that can span hours or millennia. To understand what we see in a spectrum, we must understand all of these processes and how they interact. Consider oxygen again. On Earth, oxygen is abundant because plants and algae produce it faster than it can be consumed by chemical reactions. But oxygen is reactive. It wants to bond with other elements. It rusts iron, burns organic matter, combines with hydrogen to form water. Left to itself, without constant replenishment, atmospheric oxygen would disappear in about 4 million years, a blink in geological time. The fact that Earth's atmosphere contains so much oxygen is a profound disequilibrium, a sign that something is working against the natural tendency toward equilibrium. That something is life. But on a super-Earth, the same signature might have a different meaning. If the planet has no magnetic field and its star is blasting it with ultraviolet light, water molecules in the upper atmosphere might be split into hydrogen and oxygen. The hydrogen, being light, escapes into space. The oxygen, being heavier, stays behind. Over time, this process could build up significant amounts of oxygen even without biology. This is called abiotic oxygen production, and it is a major challenge for biosignature detection. To distinguish between biological and abiotic oxygen, scientists need additional clues. They look for other gases that should not coexist with oxygen unless life is present. They model the planet's atmosphere, calculating how much oxygen could accumulate from photolysis alone. They search for signs of surface water, vegetation patterns, seasonal variations, anything that might tip the scales toward a biological explanation. Methane adds another layer of complexity. On Earth, most methane comes from life, from microbes in wetlands and oceans, from the digestive systems of animals, from decomposing plants. But methane can also come from volcanoes, from hydrothermal vents, from chemical reactions between water and certain minerals deep underground. On a super-Earth with active geology, these abiotic sources might produce large amounts of methane. To claim a biological origin, scientists would need to show that the methane is accompanied by other biosignatures, that its concentration is higher than geological processes alone could explain, or that it varies in ways consistent with life, such as seasonal cycles linked to changes in temperature or sunlight. The concept of a biosignature pair becomes important here. A biosignature pair is a combination of gases that are difficult to explain without biology. Oxygen and methane together are a classic example. In an atmosphere, these two gases react with each other, forming carbon dioxide and water. For both to persist at detectable levels, something must be constantly producing them. On Earth, that something is the combination of photosynthetic organisms producing oxygen and methanogenic microbes producing methane. Finding the same pair on a super-Earth would be strong evidence of life, though not absolute proof. Scientists would still need to rule out exotic geochemical scenarios, unusual photochemistry, or other processes we have not yet imagined. Other biosignature pairs are being proposed. Oxygen and nitrous oxide could be another, as nitrous oxide is produced by soil bacteria and is hard to generate in large quantities through abiotic processes. Phosphine and oxygen might work, though phosphine's origins are still debated even on Earth. Dimethyl sulfide, produced by marine plankton, could serve as a biosignature if detected alongside oxygen or water vapor, as it is highly reactive and should not persist in an oxidizing atmosphere unless continuously replenished. The challenge is that these gases are often present at much lower concentrations than oxygen or methane, making them harder to detect with current instruments. Future telescopes, with larger mirrors and more sensitive spectrographs, will be needed to search for these rarer signals. There is also the possibility of detecting life through seasonal variations. On Earth, the concentration of carbon dioxide in the atmosphere rises and falls each year as plants grow and die, absorbing carbon dioxide in summer and releasing it in winter. This creates a measurable annual cycle. If a super-Earth has vegetation, or something analogous, it might show similar cycles in its atmospheric composition. By observing the planet repeatedly over months or years, astronomers could look for these patterns. A signal that waxes and wanes with the planet's orbit, that correlates with changes in temperature or sunlight, would be a compelling hint of biology. But it would also require many observations, more time than any single telescope can spare for a single target, and so this approach will likely be used only for the most promising candidates. Then there are the false negatives, the ways we might miss life even when it is present. Life on Earth has changed dramatically over its history. For the first 2 billion years, the atmosphere contained almost no oxygen. Photosynthesis had evolved, but it was a different kind, one that did not release oxygen as a byproduct. Only after cyanobacteria appeared did oxygen begin to accumulate, and even then it took hundreds of millions of years to reach modern levels. If we observed Earth during its early history, we would not detect oxygen. We might detect methane, produced by archaea, but without oxygen alongside it, we might dismiss the signal as geological. A super-Earth in a similar stage of development might host abundant microbial life that leaves no clear biosignature. We would look right at it and see nothing. There is also the question of exotic biochemistries. Life on Earth is based on carbon, uses water as a solvent, and relies on a handful of key elements like nitrogen, phosphorus, and sulfur. But other chemistries are possible, at least in theory. Silicon-based life, ammonia-based life, life that thrives in liquid methane or hydrogen sulfide, these are speculative but not impossible. Such life might produce gases we would not recognize as biosignatures. It might operate in temperature ranges or chemical environments we consider hostile. It might be invisible to our current search methods, hiding in plain sight because we are looking for the wrong signals. This is a humbling thought. We are searching for life as we know it, because that is the only kind we understand. But the universe is vast and strange, and it may have found other solutions to the problem of existence. Even with all these uncertainties, the search continues. Scientists refine their models, testing them against laboratory experiments and observations of Earth's own atmosphere. They catalogue false positive scenarios, building databases of abiotic processes that could mimic life. They develop new detection methods, new ways to tease apart overlapping signals, new algorithms that can sift through noisy data to find patterns. The goal is not to jump to conclusions, but to build a case, piece by piece, until the evidence is overwhelming. A single detection of oxygen or methane will not be enough. But multiple gases in disequilibrium, seasonal variations, a composition that matches no known abiotic process, that might be enough. That might be the proof we need. And if that proof comes, if we find ourselves staring at a spectrum that can only be explained by life, then the question Stephen Hawking asked will take on new urgency. Are we ready for that knowledge? Are we prepared for what it might mean, not just scientifically, but philosophically, politically, emotionally? The discovery of microbial life on a super-Earth might seem benign, but it would shatter the illusion of human uniqueness. It would confirm that biology is common, that given the right conditions, life emerges, perhaps inevitably. And if life is common, then intelligence might be too. Somewhere in the galaxy, perhaps on one of these super-Earths, perhaps on a world we have not yet discovered, there might be beings looking back at us, reading our atmosphere, wondering if we are alone, wondering if they should make contact. For now, we work with the chemistry we have. We measure, we model, we wait. And in the waiting, we learn patience, humility, and the slow, careful discipline of science. Part 8. The Shadow of the Unknown. The search for life beyond Earth is often framed as a hopeful endeavor, a quest for connection, a reaching out toward the cosmos in the spirit of curiosity and wonder. But there is another thread woven through this narrative, one that is quieter, more cautious, tinged with unease. It is the awareness that discovery is not always benign, that finding what we seek might bring complications we are not prepared to face. Stephen Hawking voiced this concern repeatedly in the later years of his life, warning that humanity should be wary of announcing its presence to the universe. His reasoning was simple and sobering. History teaches us that when civilizations with vastly different levels of technology meet, the outcome is rarely good for the less advanced. Hawking was not speaking of hostile aliens in the way science fiction often portrays them, as tentacled monsters or warlike empires bent on conquest. His concern was more subtle and more chilling. He imagined advanced civilizations that might view us the way we view less complex life forms, as resources to be exploited or obstacles to be removed. A civilization capable of interstellar travel would possess technology far beyond our own, technology we cannot predict or defend against. They might need our planet for its resources, its water, its minerals, its position in space. They might see us as we see ants, something to be worked around or eliminated if convenient. Intent might not even matter. The simple fact of their arrival could be catastrophic, bringing diseases, disrupting ecosystems, or altering the balance of power in ways that leave humanity diminished or destroyed. This is not paranoia. It is extrapolation from our own history. When European explorers reached the Americas, they brought with them diseases that killed millions of indigenous people who had no immunity. When colonial powers encountered less technologically advanced societies, they subjugated them, extracted their resources, and imposed their own systems of governance and belief. The intentions varied. Some colonizers believed they were bringing civilization, progress, enlightenment. Others were openly exploitative. But the result was the same. The weaker party suffered. Hawking wondered if the same dynamic might play out on a cosmic scale, with Earth in the role of the colonized rather than the colonizer. The question becomes even more complex when we consider intelligence. Microbial life on a super-Earth is one thing. It poses no threat. It cannot reach us, cannot harm us, cannot even know we exist. But intelligent life, life capable of technology, communication, perhaps even space travel, that is a different matter entirely. If we detect biosignatures on a super-Earth and later discover that those biosignatures are accompanied by signs of industry, artificial lights on the night side, radio emissions, megastructures in orbit, then we would know we are not alone in a much more immediate sense. And they, observing us with their own telescopes, would know the same. The question then becomes, what do we do with that knowledge? Do we try to communicate? Do we stay silent, hoping they have not noticed us? Do we prepare for the possibility of contact, whether friendly or hostile? Some scientists argue that contact is unlikely to be hostile. They point out that any civilization advanced enough to travel between stars would have solved the problems that lead to violence. They would have abundant resources, advanced technology, stable societies. They would have no need to conquer or exploit. Intelligence, they argue, brings with it a capacity for empathy, cooperation, ethics. A civilization that survives long enough to reach the stars must have transcended the tribalism and violence that mark humanity's history. This is an optimistic view, and it may be correct. But it is also an assumption, and assumptions can be dangerous. There is also the possibility that advanced civilizations are common but silent. This is one proposed solution to the Fermi paradox, the puzzle of why we have not yet detected any signs of extraterrestrial intelligence despite the vastness of the universe and the apparent abundance of potentially habitable planets. Perhaps intelligent species arise frequently, but they learn, through experience or caution, to keep quiet. They observe but do not reveal themselves. They listen but do not broadcast. They know that the universe might be populated by others like them, or by others far less benign, and so they practice a kind of cosmic discretion. If this is true, then our own efforts to search for life, to send signals into space, to announce our presence, might be seen by these silent watchers as reckless, naive, or even suicidal. Hawking's warning gains weight when we consider how little we know about the motivations and values of a truly alien intelligence. Human ethics are shaped by our biology, our evolution, our history. We value life because we are alive. We value cooperation because we are social animals. We value freedom because we have experienced oppression. But an intelligence that evolved under different conditions, on a world with different chemistry, different gravity, different ecosystems, might value entirely different things. It might not recognize us as beings worthy of moral consideration. It might see the universe in ways we cannot comprehend, operate according to principles we cannot predict. Communication itself might be impossible, not because of language barriers, but because our modes of thought are too different to bridge. This leads to a darker possibility, one that some researchers have explored. What if advanced civilizations are not just silent, but predatory? What if the universe is populated by intelligences that survive by consuming others, by extracting resources from inhabited worlds, by eliminating potential competitors before they become threats? This idea, sometimes called the dark forest hypothesis, suggests that the cosmos is a dangerous place, where revealing your location is a fatal mistake. In this view, the silence we observe is not a choice but a necessity. Species that broadcast too loudly are found and destroyed. Those that survive are the ones who learn to hide. If this hypothesis is correct, then our search for life, and the signals we have already sent into space, might have marked us as targets. Most scientists find this scenario unlikely, if only because it requires a level of universal malevolence that seems inconsistent with the diversity we observe in nature. But unlikely is not impossible. And even if most civilizations are benign, it only takes one malevolent actor to pose a threat. This is why some researchers advocate for caution in our attempts to contact extraterrestrial intelligence. They argue that we should listen before we speak, that we should observe before we reveal ourselves, that we should understand the risks before we take actions that cannot be undone. The study of super-Earth atmospheres, then, is not just a scientific endeavor. It is also a reconnaissance mission, a way of learning what is out there before deciding how to proceed. If we detect biosignatures on a distant world, we will know that life exists elsewhere. But we will not yet know whether that life is simple or complex, whether it is alone or shares its world with intelligence, whether it is peaceful or dangerous. We will have answered one question, but opened a dozen more. And each of those questions will carry weight, will demand careful thought, will require us to consider not just what we want to find, but what we are willing to risk in the finding. There is also the question of how such a discovery would affect us, here on Earth, regardless of whether the life we find poses any physical threat. The confirmation that we are not alone would ripple through every aspect of human culture. Religions would grapple with the theological implications. Philosophers would revise their understanding of consciousness and existence. Politicians would debate how to respond, whether to unify in the face of cosmic companionship or fracture over questions of priority and purpose. The discovery could inspire hope, a sense of connection to something larger. Or it could inspire fear, a realization that we are small and vulnerable in a universe that does not revolve around us. The impact would depend not just on what we find, but on how we interpret it, how we communicate it, and how we choose to move forward. Stephen Hawking did not advocate for abandoning the search. He was a scientist, and scientists seek knowledge even when that knowledge is uncomfortable. But he did advocate for caution, for thinking carefully about the consequences of our actions, for recognizing that the universe is vast and we are small, and that our survival may depend on humility as much as on curiosity. As we peer into the atmospheres of super-Earths, as we decode the gases and search for signs of life, we carry this tension with us. The hope of discovery, the weight of uncertainty, the knowledge that what we find might change everything, for better or worse, and that once we know, we cannot unknow. The night sky is filled with stars, and around those stars are worlds, and on some of those worlds there may be life. This is no longer speculation. It is becoming observation. And as the observations accumulate, as the data grows richer and the instruments more powerful, we move closer to the moment when speculation becomes certainty. What we do with that certainty, how we respond to it, whether we greet it with joy or trepidation, will say as much about us as it does about the life we find. For now, we watch, we measure, we wonder, and we prepare, as best we can, for a universe that is more complex, more populated, and more uncertain than we ever imagined. Part 9. The long view across deep time. When we search for life on super-Earths, we are not just looking across space. We are also looking across time, vast stretches of it, measured in millions and billions of years. The light we collect from these distant worlds left their surfaces long before we were here to receive it. A super-Earth 40 light-years away shows us what its atmosphere was like 40 years ago. One 1,000 light-years away reveals conditions from a time before the printing press, before agriculture, before humans walked upright on the African savanna. We are observers of the past, reading messages that were written and sent before we existed to read them. And this introduces another layer of complexity to our search, another dimension of uncertainty. Life on Earth has existed for at least 3.5 billion years, but it has not remained static. It has evolved, adapted, transformed the planet in waves of change that rippled through ecosystems and atmospheres alike. The early Earth was a different world, with a different sky, different oceans, different chemistry. For most of its history, Earth's atmosphere contained no free oxygen. The sky would have been orange or pink, tinted by methane and other hydrocarbons. The land was barren rock, devoid of plants or soil. Life existed only in the water, single-celled organisms that fed on chemicals dissolved in the sea or produced by volcanic vents. They left no biosignatures we would easily recognize today. No oxygen, no forests, no seasonal cycles of growth and decay. If an alien astronomer had observed Earth 3 billion years ago, they might have concluded it was lifeless, or at best, ambiguous. Then came the Great Oxidation Event, a slow catastrophe that unfolded over hundreds of millions of years. Cyanobacteria, a new kind of microbe capable of photosynthesis, began producing oxygen as a waste product. At first, the oxygen was absorbed by iron dissolved in the oceans, rusting it out and forming vast deposits of banded iron formations that we mine today. But eventually, the oceans became saturated. Oxygen began to accumulate in the atmosphere. For the anaerobic organisms that had dominated life up to that point, oxygen was poison. It caused a mass extinction, wiping out countless species and fundamentally altering the trajectory of evolution. But it also opened new possibilities. Aerobic respiration, the process of using oxygen to extract energy from food, is far more efficient than anaerobic pathways. It allowed organisms to grow larger, more complex, more active. It paved the way for everything that came after, from multicellular algae to fish to dinosaurs to us. This history matters when we think about super-Earths. A planet might be teeming with life, but if that life has not yet evolved oxygen-producing photosynthesis, we might not detect it. A planet might have had life for billions of years, but if it is still in its pre-oxygen phase, its atmosphere might look barren to our instruments. We would be looking at a living world and not recognizing it. This is the problem of timing. Life takes time to evolve, to diversify, to reshape its environment. The window during which a planet displays clear, detectable biosignatures might be narrow, a fraction of its total history. We might be looking at the right planet at the wrong time, either too early, before life has left its mark, or too late, after it has gone extinct or evolved beyond the signatures we know how to find. Extinction is another concern that stretches across deep time. Life on Earth has survived for billions of years, but it has come close to ending many times. There have been 5 major mass extinctions, events that wiped out the majority of species and reshaped the biosphere. The causes varied: asteroid impacts, volcanic eruptions, climate shifts, ice ages, changes in ocean chemistry. Each time, life recovered, but the recovery took millions of years, and the forms that emerged were different from what came before. A super-Earth might go through similar cycles: periods of abundance followed by collapse, long stretches of recovery, new radiations of diversity. If we observe such a planet during a low point, after mass extinction but before recovery, we might see only faint traces of life, not enough to be certain. There is also the possibility that life on some planets never advances beyond the microbial stage. On Earth, it took nearly 3 billion years for multicellular life to evolve, and even then, the transition was not guaranteed. It required specific conditions, specific innovations in cellular machinery, perhaps even specific accidents of chemistry or environment that might not occur elsewhere. Single-celled life is remarkably resilient. It can survive extreme heat, extreme cold, high radiation, low nutrients. It can persist in subsurface aquifers, in ice, in rock, waiting out periods of hardship. But it does not build cities or send radio signals or reflect light in ways that stand out from a distance. If most life in the universe remains microbial, then biosignatures, subtle and hard to interpret, might be all we ever find. No megastructures, no technosignatures, just faint chemical whispers that hint at biology without confirming complexity. And then there is the question of longevity. How long does a technological civilization last? Humans have had industrial technology for a few centuries, radio technology for just over a century, space technology for less than a century. In cosmic terms, this is an eye blink. If we destroy ourselves through war, environmental collapse, or some other catastrophe, our window of detectability will have been incredibly brief. An alien astronomer observing Earth 1,000 years from now might see no signs of technology, no artificial lights, no radio transmissions, just a planet recovering from whatever we did to it. The same might be true of civilizations on super-Earths. They might arise, flourish, and vanish in timescales so short that the odds of us observing them during their technological phase are vanishingly small. We might be looking at worlds that once had civilizations, or that will have them in the future, but that are silent now, in the gap between eras. This is one formulation of the Fermi paradox. If intelligent life is common, and if civilizations last for millions of years, then the galaxy should be teeming with detectable signals. The fact that we see none suggests either that intelligent life is rare, or that it does not last long, or that it chooses not to broadcast, or that we are looking in the wrong ways. Each possibility has profound implications. If intelligence is rare, then we are precious, perhaps unique, and our survival matters on a cosmic scale. If civilizations are short-lived, then the universe is a graveyard of failed experiments, and we are running out of time to avoid the same fate. If civilizations are silent by choice, then the galaxy might be full of watchers, and we are the noisy newcomers blundering into a community that has learned the value of discretion. Stephen Hawking leaned toward the latter interpretation. He believed that advanced civilizations likely exist but remain hidden, either because they have learned caution or because those that did not are no longer around to broadcast. In this view, the silence of the cosmos is not emptiness but strategy, and our own broadcasts, the radio and television signals that have been leaking into space for over a century, might be a mistake, a beacon that attracts attention we do not want. Some scientists have proposed sending deliberate messages to nearby stars, powerful transmissions designed to be noticed. Hawking and others have argued against this, saying that we should listen first, observe, learn what is out there before announcing ourselves. The debate continues, unresolved, a question of risk and reward that has no clear answer. But even without deliberate broadcasts, we are making our presence known. Our atmosphere is changing. The concentration of carbon dioxide is rising, the result of burning fossil fuels. Methane levels are increasing. Industrial pollutants, chemicals that do not exist in nature, are accumulating. An advanced civilization observing Earth with sufficiently sensitive instruments could detect these changes. They would see a planet whose atmosphere is being altered by its inhabitants, a signature not of natural biology but of industrial activity. This is a techno-signature, and it makes us visible even if we are not trying to be. If we can imagine detecting such signatures on super-Earths, then we must accept that others might detect them in us. We are already part of the cosmic conversation, whether we intended to be or not. The long view across deep time reminds us that the universe operates on scales that dwarf human experience. Civilizations rise and fall. Species evolve and go extinct. Planets are born from dust and die when their stars swell into red giants. The light we see from distant worlds is old light, carrying information from the past, and by the time we receive it, the conditions it describes may have already changed. A super-Earth that showed biosignatures 100 years ago, when the light we are now detecting left its atmosphere, might be dead now. Its life extinguished by a stellar flare or an asteroid impact or a runaway climate shift. Or it might have evolved, its biosignatures changed, its atmosphere transformed by new forms of life we would not recognize. We are chasing ghosts, in a sense, trying to read the history of worlds that are no longer exactly as we see them. This does not make the search futile. It makes it poignant. We are reaching across the void, not just of space but of time, trying to connect with something that might be gone, or might not yet exist, or might be watching us with the same uncertainty we feel. We are part of a story that is unfolding on timescales we can barely comprehend, and our observations are snapshots, moments frozen in light, pieces of a much larger narrative. The answers we seek might not come in our lifetimes, or our children's lifetimes, or their children's. But we search anyway, because the question matters, because the universe is asking it, and because somewhere in the depths of time and space, there might be an answer waiting to be found. As we move forward, we will consider what this search means for us, not just as scientists but as a species, and how it shapes our understanding of our place in the cosmos. Part 10. What the search reveals about ourselves. The search for life on super-Earths is often described as an outward journey, a reaching toward the stars, an exploration of the unknown. But it is also an inward journey, a process of self-discovery that reveals as much about humanity as it does about the cosmos. Every telescope we build, every spectrum we analyze, every hypothesis we test, reflects our values, our fears, our hopes, our limitations. We are not neutral observers. We are participants, shaped by our history and our biology, asking questions that arise from our particular place in space and time. And in trying to understand alien worlds, we are also trying to understand ourselves. Consider what it means to search for biosignatures. We are looking for life as we know it, because that is the only life we have experience with. We search for oxygen, methane, water vapor, the chemical markers of Earth's biology. But this approach is inherently biased. It assumes that life elsewhere will resemble life here, that it will use the same molecules, the same processes, the same logic. This might be true. Carbon is abundant, water is common, and the laws of chemistry are universal. If there is a best way to build life, evolution might discover it repeatedly, converging on similar solutions across many worlds. But it might not be true. Life might be more diverse, more inventive, more strange than we can currently imagine. By focusing on familiar biosignatures, we risk missing life that operates differently, that leaves different traces, that would be invisible to our current methods. This bias is not a flaw. It is a necessity. We must start somewhere, and starting with what we know is the only practical approach. But it is worth acknowledging, worth keeping in mind as we interpret our findings. The absence of familiar biosignatures does not mean a planet is lifeless. It might mean we are looking for the wrong things, asking the wrong questions. Humility is important in this search, the recognition that we are beginners, that the universe is older and larger and more complex than our models can capture. Every observation is a chance to learn, to refine our understanding, to expand the boundaries of what we consider possible. The search also forces us to confront our own fragility. When we study how atmospheres are lost, how planets become uninhabitable, how life can be extinguished by stellar flares or asteroid impacts or climate shifts, we are also studying our own vulnerabilities. Earth's atmosphere is a thin shell, a delicate balance of gases that could be disrupted by any number of events. Our magnetic field protects us, but it has weakened and reversed many times in Earth's history, and it could do so again. Our sun is stable, but it will not remain so forever. In about 1 billion years, it will brighten enough to boil away our oceans, rendering Earth uninhabitable. In 5 billion years, it will swell into a red giant, engulfing the inner planets. These are distant threats, but they are real, and they remind us that habitability is temporary, that the conditions we take for granted are the product of a specific moment in cosmic history. This awareness shapes how we think about our future. If Earth will not always be habitable, then survival in the long term requires us to become a multi-planet species, to spread beyond this world before it becomes unable to support us. The study of super-Earths is not just about finding life elsewhere. It is also about understanding what makes a planet habitable, so that we might one day identify worlds we could migrate to, or terraform, or at least observe as cautionary tales or sources of inspiration. This pragmatic dimension sits alongside the philosophical one, the desire to know if we are alone, blending with the need to ensure we do not remain confined to a single, fragile world. The search also raises questions about our responsibilities. If we find life on a super-Earth, do we have a duty to protect it, even from a distance? Do we have a right to study it, to probe its atmosphere, to send signals in its direction? These are not just academic questions. As our technology improves, as we develop the ability to image exoplanets directly, to resolve surface features, to detect continents and oceans and perhaps even vegetation patterns, we will be peering into these worlds with increasing intimacy. If life is there, it will not have consented to being observed. It will not know we are watching. The ethical implications are murky, and there is no consensus on how to navigate them. Some argue that observation is passive, that we are merely collecting photons that would have traveled into space regardless. Others argue that knowledge brings responsibility, that once we know life exists on a world, we have a duty to consider how our actions, including potential future contact, might affect it. Then there is the question of how a discovery would change us. The confirmation of life beyond Earth would be one of the most significant events in human history. It would unite us in the knowledge that we are not alone, that biology is a cosmic phenomenon, that the universe is more alive than we thought. But it might also divide us. Different cultures, different religions, different political systems would interpret the discovery in different ways. Some would see it as proof of divine creation, evidence that a creator seeded life throughout the universe. Others would see it as confirmation that life is a natural process, requiring no supernatural explanation. Some would advocate for reaching out, for attempting communication. Others would counsel caution, or even isolation. The discovery would not answer all our questions. It would create new ones, and the debates over how to respond could be as contentious as any issue we currently face. Stephen Hawking's warning adds another layer to this introspection. His concern was not just about the danger of hostile aliens, but about the danger of our own naivety. Humanity has a tendency toward optimism, a belief that things will work out, that contact with other intelligences would be beneficial, enlightening, a step forward. But history does not always support this optimism. We have made mistakes before, acted without fully considering the consequences, and paid the price. Hawking was urging us to think carefully, to consider the risks alongside the rewards, to approach the unknown with both curiosity and caution. This is not pessimism. It is realism, grounded in an understanding of how the universe works and how unpredictable first contact can be. The search for life on super-Earths is also a mirror. It reflects our desire to connect, to find meaning beyond our immediate surroundings, to know that we are part of something larger. Humans are social beings. We form communities, build relationships, seek out others who share our experiences. The idea of finding life elsewhere taps into this deeply rooted need. It suggests that the universe is not empty, not indifferent, not silent. It promises that somewhere, on some distant world, there are beings who face the same challenges we do, who look up at their sky and wonder if they are alone, who might one day know that we exist and that we wondered about them too. This is a powerful emotional driver, and it fuels the search as much as any scientific rationale. But the mirror also shows us our limitations. We are creatures of a single planet, a single star, a single moment in time. Our perspective is narrow. Our instruments, no matter how advanced, can only see so much. Our theories, no matter how elegant, are always incomplete. The search for life is an exercise in humility, a reminder that the universe does not revolve around us, that we are learners, explorers, questioners, but not yet knowers. Every discovery is provisional, every conclusion open to revision. And that is how it should be. Science thrives on uncertainty, on the willingness to admit when we do not know, to keep searching, to remain open to surprises. As we study super-Earths, as we decode their atmospheres and search for signs of life, we are also defining what it means to be human in the age of exoplanet discovery. We are deciding what values we will carry with us as we reach beyond Earth, what questions we will ask, what risks we are willing to take, and what kind of future we want to build. The answers are not predetermined. They will emerge from the choices we make, the priorities we set, the ways we balance hope with caution, curiosity with responsibility. And in making those choices, we are shaping not just our understanding of the universe, but our place within it. The search continues, night after night, as telescopes across the world and in space turn toward distant stars. The data accumulates. The models improve. The questions sharpen. And somewhere, on a super-Earth orbiting a star we have named and catalogued, perhaps there is life, unaware that we are looking, unaware that its atmosphere is being read, its secrets slowly unraveled by beings it will never meet. Or perhaps there is nothing, just rock and gas and silence. Either answer will teach us something profound. Either answer will change us. And so we watch and wait and wonder, because that is what we do, and because the universe, in its vastness and mystery, invites us to keep looking. Part 11. The instruments of tomorrow and questions they will answer. The telescopes we have today are remarkable, but they are only the beginning. The James Webb Space Telescope, the ground-based giants under construction, the spectrographs that parse light into its component wavelengths, these are the first generation of tools designed specifically to study exoplanet atmospheres. They have given us our initial glimpses, our first tentative readings of alien skies. But they are limited by their size, their sensitivity, their ability to distinguish faint signals from noise. To truly understand super-Earths, to search for biosignatures with confidence, to map their climates and probe their surfaces, we need the next generation. We need instruments that have not yet been built, missions that are still being planned, technologies that are being tested in laboratories and observatories around the world. One of the most ambitious projects on the horizon is the Habitable Worlds Observatory, a space telescope designed to directly image Earth-like planets and super-Earths around nearby stars. Unlike Webb, which primarily observes transits and measures atmospheres indirectly, this new observatory would capture the light from planets themselves, separating it from the overwhelming glare of their parent stars. To do this, it will use a coronagraph far more advanced than anything currently in operation, a device that blocks starlight with extreme precision while allowing the planet's faint glow to pass through. The telescope would study dozens of targets over the course of its mission, building a catalogue of habitable worlds, measuring their atmospheric compositions, searching for the telltale signs of oxygen, methane, water vapor, and other biosignatures. The technology required for this mission is daunting. The coronagraph must suppress starlight by a factor of 10 billion, allowing the observatory to detect a planet that is 1 billion times fainter than its star. The mirror must be perfectly smooth, with imperfections measured in nanometers. The instruments must be stable, shielded from vibrations, temperature fluctuations, and other sources of noise. The mission must launch, travel to its observing position, unfold, calibrate, and operate flawlessly for years or decades. Any failure, any flaw, could compromise the entire endeavor. But the potential rewards justify the effort. If successful, the Habitable Worlds Observatory would give us our first true portraits of Earth-like worlds, images and spectra that could confirm the presence of life beyond our solar system. On the ground, the extremely large telescope and its siblings will complement these space-based observations. With mirrors tens of meters across, these telescopes will have the light-gathering power to study fainter, more distant targets. They will observe in wavelengths that space telescopes cannot, filling in gaps in the data. They will use adaptive optics, systems that measure and correct for the distortions caused by Earth's atmosphere, allowing them to achieve resolutions that rival or exceed those of space-based instruments. They will work in concert with space telescopes, cross-checking results, providing independent confirmation, ensuring that no single instrument's quirks or limitations lead to false conclusions. There are also proposals for more exotic missions. The LIFE mission, a European concept, would use a fleet of small infrared telescopes flying in formation, combining their light to create an interferometer with an effective aperture far larger than any single telescope could achieve. This formation flying is technically challenging, requiring precise positioning and coordination, but it would allow the mission to detect the faint thermal emission from rocky planets in the habitable zone, measuring their temperatures and atmospheric compositions even when they do not transit their stars. Another concept, the Habitable Exoplanet Observatory, or HabEx, would pair a space telescope with a massive external starshade, a flower-shaped screen tens of meters across that would fly thousands of kilometers ahead of the telescope, blocking starlight before it even reaches the optics. This approach avoids some of the challenges of coronagraphs, though it introduces others, such as the need to position and maneuver the starshade with extraordinary precision. Each of these missions is years or decades away from launch. They require funding, political support, technological breakthroughs, and sustained effort from thousands of engineers, scientists, and administrators. They compete with other priorities, other missions, other questions that also deserve answers. But they represent the trajectory of the field, the direction we are moving, the tools we will need to answer the questions that current instruments can only begin to address. And as we wait for these missions to be built and launched, we continue to refine our methods, testing them on the planets we can observe now, learning what works and what does not, preparing for the flood of data that will come when the next generation of telescopes comes online. There is also progress in data analysis. The spectra we collect from exoplanet atmospheres are complex, filled with overlapping signals, noise, instrumental artifacts, and the contributions of stars, planets, and interstellar dust all mixed together. Extracting the planetary signal requires sophisticated algorithms, statistical methods, and increasingly, machine learning. Researchers are training neural networks to recognize the patterns of biosignatures, to distinguish between biological and abiotic signals, to flag anomalies that might indicate something unexpected. These algorithms are not perfect. They can be fooled by noise, biased by their training data, or limited by the assumptions built into their design. But they are improving, and they are allowing scientists to process data faster and more thoroughly than ever before. Machine learning is also being used to prioritize targets. With thousands of known exoplanets and more being discovered every month, astronomers cannot study them all in detail. They need to focus on the most promising candidates, the planets most likely to be habitable, most likely to show biosignatures, most accessible to observation. Machine learning models can analyze the properties of known planets, their sizes, masses, orbits, and the characteristics of their stars, and predict which ones are most worth studying. These predictions are probabilistic, not certain, but they help direct limited telescope time toward the targets with the highest potential payoff. There is also the question of how we will communicate our findings. If we do detect biosignatures on a super-Earth, the announcement will be one of the most significant in human history. It will need to be communicated carefully, with appropriate context, with acknowledgement of uncertainties, with sensitivity to the ways different audiences will interpret it. Scientists are already thinking about these protocols, developing guidelines for how to verify findings, how to seek independent confirmation, how to present results to the public and to policymakers. The goal is to avoid premature announcements, to ensure that any claim of discovering life is robust and defensible, and to manage expectations so that the public understands both the significance and the limitations of what has been found. The instruments of tomorrow will also allow us to study phenomena we can barely detect today. Exomoons, moons orbiting exoplanets, might themselves be habitable, particularly if they orbit gas giants in the habitable zone and have enough internal heat to maintain liquid water beneath icy surfaces. Exocomets and exoasteroids, the debris that orbits stars, could deliver water and organic molecules to planets, seeding them with the ingredients for life. Planetary rings, magnetic fields detected through their interaction with stellar wind, volcanic activity inferred from atmospheric chemistry. These are all pieces of the puzzle that future instruments will help us see more clearly. And beyond biosignatures, there are technosignatures, the signs of intelligent life and its activities. These might include industrial pollutants in an atmosphere, chemicals that do not occur naturally. They might include artificial lights on the night side of a planet, a signature that could be detected with sufficiently sensitive imaging. They might include megastructures, enormous constructions that block or redirect starlight in ways that are hard to explain with natural processes. They might include radio transmissions, deliberate or accidental, leaking into space and waiting to be intercepted. The search for technosignatures is a distinct field, often called SETI, the search for extraterrestrial intelligence, but it overlaps increasingly with exoplanet science as our ability to study planets improves. Stephen Hawking's concerns weigh heavily here. If we detect a technosignature, if we find evidence of an advanced civilization on a super-Earth or any other world, the question of how to respond becomes urgent. Do we reply? Do we stay silent? Do we assume that any civilization advanced enough to build detectable technology is also wise enough to be peaceful? Or do we assume the opposite? There is no consensus, and the debate is ongoing. Some scientists argue that we should establish international protocols now, before a detection occurs, so that we are not making hasty decisions in the heat of the moment. Others argue that such protocols are premature, that we should wait until we have actual data before deciding how to respond. The instruments of tomorrow will bring us closer to these questions. They will sharpen our view of distant worlds, reveal details we can only imagine today, and force us to confront the implications of what we find. They will test our assumptions, challenge our theories, and perhaps, if we are lucky, deliver the answer we have sought for so long. The confirmation that life exists beyond Earth. The knowledge that we are not alone. And with that knowledge will come responsibility, the need to decide what we do next, how we interpret our place in a universe that is suddenly more crowded, more complex, more alive than we thought. For now, we prepare. We build the instruments. We refine the techniques. We train the next generation of scientists who will operate these telescopes and analyze their data. And we wait, with patience and anticipation, for the moment when the cosmos reveals one of its deepest secrets. Part 12. Drifting towards sleep beneath uncharted skies. As we come to the end of this journey through the atmospheres of super-Earths, through the chemistry of biosignatures and the caution of distant contact, it is worth pausing to consider where we are and where this path might lead. We have traveled far in thought, across light years and billions of years, through hypothetical skies and speculative futures. We have examined the gases that might whisper life, the forces that shape planets, the instruments that read distant worlds, and the questions that linger in the spaces between what we know and what we hope. And now, as the night deepens and the stars turn overhead, we can let these thoughts settle, gently, like dust falling through still air. The search for life beyond Earth is not a single question but a constellation of them, each connected to the others, each illuminating a different facet of existence. Are we alone? What is life? How common is it? What forms might it take? What does it mean to be conscious, to be intelligent, to wonder about one's place in the cosmos? These are questions humans have asked for as long as we have had language, perhaps longer. But only in the last few decades have we had the tools to begin answering them with data rather than speculation. The discovery of exoplanets transformed the search from philosophy to science, from myth to measurement. And the study of super-Earths, with their tantalizing potential for habitability, has brought us to the threshold of a discovery that could redefine our understanding of ourselves and our universe. But thresholds are uncertain places. We stand at the edge, looking across, not yet sure what lies on the other side. We have found thousands of planets, dozens of them potentially habitable, a handful that show hints, faint and ambiguous, of conditions that might support life. We have not yet found the definitive biosignature, the unambiguous signal that can only be explained by biology. We have not yet answered the question. And so we remain in a state of suspension, between ignorance and knowledge, between solitude and companionship, waiting for the data to tip us one way or the other. This waiting is not passive. It is filled with work, with observation, with analysis, with the slow accumulation of evidence. Every night, telescopes around the world and in space turn toward distant stars. Every day, researchers sift through data, run models, refine theories. The search is a collective effort, spanning nations and disciplines, driven by curiosity and the deep human need to understand. It is patient work, unglamorous much of the time, but it is also profound. Each observation, each spectrum, each data point, is a small step toward an answer that will resonate through all of human culture. And as we search, we carry with us the dual awareness that Stephen Hawking articulated. Hope, that we might find life, that we might discover we are part of a larger community of living worlds. And caution, that such a discovery might bring complications, that the universe might be more dangerous than we assume, that revealing our presence might carry risks we do not fully understand. These are not contradictory impulses. They are complementary, two sides of the same coin. To search with hope is to believe that knowledge is worth pursuing. To search with caution is to respect the unknown, to acknowledge that we are newcomers to this endeavor, that we have much to learn, and that humility is as important as ambition. The super-Earths we study are more than scientific targets. They are worlds, each with its own history, its own story written in rock and gas and light. Some are hellish, baked by their stars, atmospheres thick with carbon dioxide or stripped away entirely. Some are frozen, distant and dark, their surfaces locked in ice. And some, just a few, sit in that narrow range where water might flow, where temperatures are moderate, where life, if it arose, might persist. These are the worlds that capture our imagination, that draw us back again and again, that make us wonder what it would be like to stand on their surfaces, to breathe their air, to see their skies. We will never visit these worlds, not in our lifetimes, perhaps not ever. They are too far, the distances too vast, the technology required to cross interstellar space too far beyond our current capabilities. But in a sense, we are already there. The light from these planets reaches us, carrying information about their atmospheres, their temperatures, their compositions. By studying that light, we touch them, we know them, we add them to the map of reality that humanity has been building for millennia. They are no longer just points of light in the sky. They are places, distinct and particular, each with its own characteristics, its own potential, its own mysteries. And in studying them, we learn about Earth. Every planet we observe teaches us something about how worlds work, how atmospheres form and evolve, how life interacts with its environment, how fragile and resilient habitability can be. The comparisons sharpen our understanding of our own planet, of the processes that keep it habitable, of the threats it faces, of the ways we might protect or restore it. The search for life elsewhere is also a search for perspective, a way of seeing Earth not as the center of the universe but as one world among many, precious because it is ours, but not unique in kind. As the search continues, as the instruments improve, as the data accumulates, the moment of discovery draws closer. It might come next year, or in a decade, or in a century. It might come as a sudden, unambiguous detection, a signal so clear that it cannot be doubted. Or it might come slowly, through the accumulation of evidence, a growing consensus that builds over years as multiple independent observations point toward the same conclusion. However it comes, it will change us. It will confirm that life is a cosmic phenomenon, that the processes that led to our existence have occurred elsewhere, that biology is woven into the fabric of the universe. And with that confirmation will come new questions, new challenges, new opportunities to learn and grow and perhaps, eventually, to reach out. But for now, as night deepens and the mind grows quiet, it is enough to know that the search is underway. That somewhere, right now, photons are streaming from distant super-Earths, carrying information about their atmospheres, their climates, their potential for life. That those photons are being captured by telescopes, focused, split into spectra, analyzed by computers and by human minds. That the story is unfolding, slowly but surely, one observation at a time. That the universe is revealing itself, not all at once, but in whispers and hints, in patterns of light and shadow, in the language of science and mathematics and careful thought. The stars above us are not just distant suns. They are homes to planets, to worlds we are only beginning to understand. Some of those worlds might be inhabited, teeming with life, or silent and sterile. We do not yet know. But we are looking, and that looking is itself a kind of answer. It says that we are curious, that we care, that we are willing to invest time and effort and resources into understanding the cosmos. It says that we are not content with ignorance, that we reach beyond ourselves, that we ask questions even when the answers are uncertain or uncomfortable. It says that we are human, in all the complexity that word implies, with all our hope and fear, our ambition and caution, our wonder and our humility. And so we drift, gently, towards sleep, beneath skies filled with uncharted worlds. We carry with us the knowledge that the search continues, that tomorrow there will be new data, new insights, new pieces of the puzzle. We carry the awareness that we are part of something larger, a story that began billions of years ago and will continue long after we are gone. We carry the questions, unanswered but not forgotten, waiting in the quiet spaces of the mind for the moment when they might be resolved. Are we alone? What will we find? How will we respond? What does it all mean? The answers, when they come, will be written in the light of distant stars, in the atmospheres of worlds we have named and studied and wondered about. Until then, we wait, we watch, we hope, and we rest, knowing that the universe, vast and patient and full of secrets, will reveal itself in time. The search for life on super-Earths is not just a scientific endeavor. It is a conversation with the cosmos, a question asked into the void, waiting for an answer that might never come, or might arrive tomorrow, or might already be traveling toward us through the dark, patient light of space. And in asking that question, in reaching beyond ourselves, we become part of the story we are trying to uncover. We become explorers, dreamers, seekers of truth. We become, in the deepest sense, alive. Sleep well, beneath these uncharted skies. The stars will still be there in the morning, waiting. And the search will continue, gentle and persistent, as it has for all of human history and as it will for as long as we remain curious, remain hopeful, remain willing to look up and ask, what is out there? And are we ready for the answer?